check that the left and right arrows work on the keyboard.
Yeah.
Perfect. Right. Great. Okay. All right. My name is Jshs, and today I'm going to present my project Sky Wind Farm, harnessing high-altitude wind power in a scalable manner. So, wind power is primarily a function of cubic velocity. However, conventional turbines such as onshore and offshore turbines usually increase their power by increasing the cross-sectional area. That's why current turbines keep on getting larger and larger and taller and taller. OAS are a new and novel way of harnessing wind energy that seem to increase wind velocity by harnessing power at higher velocities, thus leveraging the cubic relationship with power. So, viable distribution has been used to model wind up to 99% accurately when modeling wind. And it shows that it matches very well with historical data, and viable distribution coupled with historical data indicate that wind speeds increase significantly at altitudes of 3,000 meters or more. Besides that, they also become besides that, they also are not intermittent, they become more continuous. So, the problem with current airborne wind energy systems is that they struggle to harness this power in a scalable manner. While they can produce power in the hundreds of kilowatt ranges, they struggle to harness power in the megawatt range because of how they operate, limiting their work to only research and not really useful for any practical uses. These systems are also intermittent in nature because they operate mainly below 500 meter operational altitude, where wind power isn't that continuous as a 3,000 meter. So, these systems also use horizontal axis wind turbines when operating. Horizontal axis wind turbines are turbines that rotate in this direction compared to vertical axis, which rotate in orthogonal to wind. VATs, or vertical axis wind turbines, emerge as a promising solution when harnessing high altitude wind power because they are more structurally stable, and when you're at higher altitudes, you need the stability at high altitude winds so that the material doesn't break down. In addition, one of the key features of vertical axis wind turbines is that their performance increases when you form them, whereas for horizontal axis wind turbines, when you form them, their performance significantly decreases. Those graphs indicate that relationship. So now the concept for Sky Wind Farm is to use one or more energy units, which are these things, to put at altitudes of 3,000 to 30,000 feet in the air and harness high altitude wind power in that way. The key of Sky Wind Farm is an energy unit, and each of these energy units is designed for long-term autonomous operation at high altitudes. So a Sky Wind Farm is designed to operate at high altitudes by towing to the ground, and once it's airborne, the wind turbines, vertical axis wind turbines, start converting the kinetic energy of the wind to power and transmit it through the tether. The lift wings ensure that the farm operates at high density energy layers because researchers have found that at any point in time, there will always be layers of wind velocities from 300 meter to 10,000 meter, where there will be a maximum, and the farm can adjust to that location and harness the velocity there. So it can harness the power where it's most prominent. A key feature of the energy unit is the VAT clusters, which are the vertical axis wind turbine clusters. They're in clusters because vertical axis wind turbines, as mentioned before, increase their performance when they're in clusters. I did significant research in optimizing the materials of these clusters. So the farm is 15 meters by 15 meters in diameter, and each turbine has a 3-meter diameter. However, each turbine only weighs 300 kilograms thanks to the use of composite structure using carbon fiber and hydrophobic fabric. They have also been tested to have a cutoff speed of 60 meters per second, which is quite high, and they're lightweight and efficient as mentioned before. So, another part of VAT clusters is the diffuser wall. So one of the key disadvantages of vertical axis wind turbine is that when you're operating orthogonal to the wind, you can imagine half of the time you're going against the wind, right? Diffuser walls basically block that and accelerate the wind where it hits the advantageous angles to airflow. This results in higher power, making it comparable to horizontal axis wind turbines, if not better, when formed. The tether and brittle line system, unlike other OAS systems, this system is static and transmits power from the ground and is designed to go till 10 kilometers. So, and then there's the LTA shell, which is the helium balloon. The main way the farm gains stability is through the helium balloon, and the balloon, the LTA, lighter than air gas that this uses is helium, as mentioned before. It comprises of 3 layers: a polyaminyl fluoride that acts as an environmental barrier, a polyethylene layer that acts as a physical barrier, and then a urethane layer which acts as a heat barrier. This semi-rigid structure is designed in such a way that when it goes airborne and then comes back, the pressure inside changes in such a way that the lift stays constant, and it can be used for up to 2 years without needing a helium refill, which is quite significant. The blowdown angle, the measure of the drag, the lift to drag measure of the farm, for Skyman farm is 16, which is the lowest, thanks to the helium LTA shell design and the dual lift mechanism. So the dual lift mechanism allows the farm to operate for 97.5% time in the air while producing significant amounts of power. And for the 2.5% it's not operating, it can operate crosswind to still stay in the air while not losing any power and still stay in the air. So in my research, I optimized the design through 100 different high fidelity simulations. I constructed over 8 different wind tunnel prototypes, as you can see in the picture books, and then I conducted a 6 degrees of freedom transient simulation to conduct my analysis. Let's go to the CFD simulation. So for all my simulations, I had a 26.7 velocity inlet, atmospheric pressure outlet, no slip wall, no deformation, and a rotating domain. The optimized VAT clusters were over 100 simulations were done using simulated annealing, until I came to the final configuration, which is shown here with the correct scale and correct angles. This also has optimized scale, optimized solidity, and it's optimized for the 15 to 60 meter per second wind speed ranges. For all the 100 plus simulations, I used the MSI Agate cloud computer, which gave me access to really high fidelity computers, which these simulations would not have been possible without them. For the simulations, the criteria were that y+ should be less than or equal to 1.1 over 3 million elements, and then I used the semi-implicit pressure based equations with SST K omega turbulence model. The results show that, as you can see here, this is a lone VAT turbine, and then the optimized VAT cluster that I made, it always has higher, for all the 4 turbines, they have higher power at each wind speed compared to regular turbines. These are the contours and velocities, and they have significantly higher power, up to double in some cases than the ones I constructed, which makes this really promising. This is the most optimal VAT cluster ever designed. I also did vent tunnel testing. I constructed over 8 different models, more in the picture book, and to verify my designs, along with 4 turbine, I tested 6 and 8 turbine models. And for the final model, it was a 1:20 model with the pi terms from Buckingham Pi principle, TSR, and CP. And then I used voltage and current for measuring CP and tip speed ratio to measure TSR. The results, the color is not showing well, but if you look to the back, you see 3 different colors on that screen. These are divided into 3 regions. This is the region where power was measured, and this shows alignment. We had over 95% alignment when conducting the tests through computational simulations, so this validates the simulations very well, since the physical testing matched 95% of the simulations. The total power of 15 meter by 15 meter scattering farm is 157 kilowatts, as shown here. And then I also conducted stability analysis, where I wanted to prove that this system will reject a disturbance because it's operating in the air. So for that, I used a 6 degrees of freedom transient simulation using these equations below. And the results show that once it faces a velocity disturbance, it can reorient itself to always face the direction of the wind. This has also been patented, and this balloon structure itself has been under publication. I also wanted to conduct cost analysis to show that this is an emerging renewable energy. So for my cost analysis, I used the National Renewable Energy Laboratory Tools Renewable Energy tool, and I was able to show that under 150 energy units already producing 250 production per year, the cost of each Skyline farm is only $25 per megawatt hour, which is 25% cheaper than onshore turbines, offshore turbines, and the leading 5-gen Oz. This research also, the reason why this is so, the reason why Skyline farm is so cheaper than traditional wind energy units is just because of the scale. It taps into a resource that is that is like so much more prominent that it can use way less materials. This figure is drawn to scale than a conventional turbine, but still producing the same amount of power. And the materials it uses, such as helium balloon and the vertical axis wind turbine clusters, are also not that hard to find. They are easily manufacturable. So these are the places with wind speeds that produce most of the greenhouse emissions. The ones with white are like the places that 0 to 5% of power comes from renewables. These are the places where most of the American countries live in rural regions, and the yellow regions are the places where wind energy is really slow. These are the places where sky wind farm can provide clean and clean power, since even though low altitude wind is slow and intermittent at these places, high altitude wind is not. So sky wind farm can be used here. Conventional wind turbines or solar panels cannot be, because of the duck curve. And then sky wind farm, because it operates at high altitudes, is also the first design that can function as a primary source of power. It is the first design that is designed to be scalable, the first design. It is 25% cheaper than existing Oz. It has achieved TRL of 4 and taps into 100 times larger power resource than conventional wind turbines. The design has been patented and is under publication. And thank you. I would like to thank Dr. Jshs from the University of Minnesota, Ms. Princesa Hansen for firstly allowing me to compete in this competition, and secondly telling me about science fair and Jshs. And I'd like to thank my parents for helping me support my research journey. I would like to thank you for listening.
If you're interested in optimizing cost for this process, why helium instead of hydrogen?
Yeah, that's a very good question. Actually, helium and hydrogen are basically the same price. Yes, hydrogen is cheaper, but the overall cost for this one sky wind farm is $540,000 over 20 years, and it only needs to be refilled 2 years. So it just doesn't make sense to use hydrogen since it's flammable and not as an as helium. Yes.
How high up do these have to fly? I mean, what is like that interference with airspace?
Airplanes, yeah, very good. That always comes up.
Yeah.
Air traffic. So that's not a big issue at all, because birds fly below 3,000 meters and planes fly at 11,000 meters. So airway between is mostly empty. And also birds and airplanes have like predetermined tracks, so they don't fly in like random orientations. So sky wind farm can be used at locations where birds don't fly and they don't have a history of flying. Also, they are safer than wind turbines, because wind turbines operate at like altitudes where birds fly. These are not. These don't. So yeah.
I mean, I'm trying to envision this. To me, farm, it means more than just one. So
Yeah.
how many of those would you have, I don't know, in a given area?
Yeah, very good question. So one sky wind farm, one energy unit can can power approximately 200 people. 200 people, so like a small town. Yeah, one. But the great thing about this is that, think about a coal plant. When you want to upgrade a coal plant, there's no way of like, I'm going to add 20% more power. You have to like destroy the whole building, add more. The great thing about this is that if you want to scale, so like if our community is growing, you can just add one more farm in there, and you can have farm from 1 to like over 300 in the air. And it's such high in the air that it would be enough to power an entire city.
So a farm is one. You consider
A farm is 1 to n. I call this an energy unit, and then sky wind farm is just
energy
the concept.
unit.
Yeah.
Got it. Okay.
Yeah. More questions?
How much help did you have from a mentor on this project?
That's a very good question. I didn't make a slide for that, unfortunately. But I started working on this project in 10th grade after physics class, or last semester project was to find a renewable energy that you find exciting and present it to class. I learned about airborne wind energy systems, and I was like really interested. So I independently emailed the professor at the University of Minnesota and started working like that. The idea is entirely mine. I'm also the first author, I'm the only author for the patent, and then the first author for the publication. I published this in Renewable Energy, Impact Factor 13, acceptance rate less than 10%. Anyhow, for the cost analysis, that was Dr. Jshs' idea. However, using supercomputer CFD simulations and wind tunnel testing, they were largely led by me. Other questions?